Hi, my name is Ken Hutchison. I wrote Microbiome Prescription, and this is a video version of a recent blog post. And I'm trying to do some of the more significant recent blog posts as videos because some people learn better from videos, and I tend to add additional information which can help people understand things better. So the title of the post is quite simple. Using ranges based on averages is bogus. It's incorrect. It's bad. It is not just bad science. It's bad mathematics, bad statistics. And to illustrate that one, we could be using data which came over from BioGUS site, the UK site, and we have something like 3,600 different samples. They're all processed through the identical same pipeline, and that gives us a superior, better than most people ever get hold of in clinical studies sample to be able to make use of and take a look at. Okay, so we're going to illustrate things. We're going to take a look at one particular bacteria. PM as well, call it for short to save my mangoing the pronunciation. And if we go in and take a look at it, we see what the min value is, the maximum value. Some people have 9% of the microbiome with that. They probably have some serious medical issues with that one. The median, now what is a median? The median is the value where half the people have a high value and half the people have a lower value, which is 0.254%. Quite small. But when you calculate out the average amount, it's not 0.254, it's 7.6. It is 30 times bigger than the median. In other words, you will have probably 80% of the people will have below an average amount. Not 50%, which is what people would assume, average being sort of the middle ground. Medium is the middle ground. The average or mean is much, much higher, and that's because of the nature of the data. And the mode, which is the most commonly reported number, is sitting at 12%, even higher, away from the median. Then we have things called standard deviation. 5 percentile are at 0.009%, 95 percentile are at 43%, so that's very high. Harmonic mean and geometric mean are two additional types of means which are calculated. We have something called skew and kuratose, which are of significance to people who are statisticians, but we'll just skip over that. Now, when we apply classic stats class 101 or even 201, you will get the suggestion that the reference range should be the average plus or minus 1.95 times standard deviation. In other words, between negative 21% and 36%. Wait a minute. How can you have a negative 20% of a bacteria? You can have 0% of a bacteria, but a negative 21, that should jump out like a major whoops, that something is wrong there. We can also use a box plot whiskers, and we have negative 9 to 15.8. We're not so bad for being in Never Never Land, but we also notice that the range is actually smaller than mean percent deviation. Something is off in terms of applying standard statistics to the data. Let's first of all start with what people will naively assume without checking the data. And this is the basic problem. They expect data to be a bell curve, because for a lot of things that is the case. And for bell curve, we have the mean, median, and mode being right next to each other, which is there. Now, in the real world, that doesn't always happen. Let's take a look at something like people's income. If you take a look at that, you'll find that the average income, the mean income, is perhaps 150,000 US dollars. The median may be 70,000 US dollar, and the mode, the most common value, may be 20,000 US dollars. If the earning across the population was a true bell curve, then those three values would be right on top of each other. In this case, as with the income per person in the US, it is way, way up. And so we have something being whacked. So it means that basically the classic standard statistical methodology, which tends to be taught, does not apply here. And most people are not taught because of the difficulties conceptually of dealing with oddball distributions, taught how to test for or how to handle them. Fortunately, I have a master's in statistics, is one of my specialties, and I'm a bachelor with statistics and probability were my main concentration. So the result is I look at it and say, okay, I see what the problem is, and I have the academic skills to figure out what to go wrong. Now, when you take a look at the number up above, you can see what the curve is like. I mean, it just sort of takes off to the heavens. I think I've excluded the 89 percentile here. So we have the absurd values I truncated up, but we see that it is quite a different curve than what we expect here for a bell curve. And that's where our problem begins. And what it means is there are a bunch of fancy statistical methods which could be used to do it. Here is a listing of there. And none of them are really that easy to explain, and none of them are, to the best of my knowledge, being used by any lab to determine reference ranges, which is grossly unfortunate. I, however, given my background in statistics and mathematics, spent literally a couple of years playing around with the data and then finally had a revelation which I loved, and it actually has a pending patent. It's a Coulter-Moultrie algorithm. And if we take a look at some data that comes in, definitely not a bell curve, and it's there. But so the first thing we do is we take the derivative of the slope, and now we get a blue line here. Okay, so it's we have 1, 2, 3 bumps here. We have 1, 2 bumps here. That's somewhat improved. Now we take the next derivative up, and we only have 1 bump. So we went from 3 bumps to 1 bump by doing successive derivatives of the calculated estimator for what the line is. And then 1 more, and we end up with a straight line. Oh, good. Now we can use the straight line and come to decisions that way. Where it goes off the straight line, it's become an area of concern. When it's on the straight line, it's typical behavior. So what do we find when we go in and look at actual bacteria? We do this type of process. What we end up is we end up with a large region where the estimator of a line, once it do all the appropriate derivatives, becomes almost a straight flat line. So here we have, wait a minute, if you are in this area here, you're probably too low. Simple as that. This is dropping up dramatically suddenly. So it's probably too low. Here, high, well, we don't have a major upswing. Some bacteria you have a major upswing. Here we don't, and whether or not that is going to be significant or not is a bit of a subjective there. If we adjust our parameters a little bit more, we could have the straight line going all the way to the top and having only the bottom showing up. Here is an example of a different bacteria, actually the one we started with. We have a straight line, then we have a second straight line, very different slope, and then the first straight line. So we have the low region where things seems to be abnormal. We have bacteria people seeming to be in one state, a transition which seems to be a relatively short period of time range. In other words, people in this one are probably unstable in the middle and going to eventually go up or go down. And then we have the top one, which is basically stop, and we have a tiny, tiny uptick at the very top, which could be deemed for too high. Majority of people would appear to be too, or like to be too low. but we have two straight lines, which means if we start adding in metadata as a symptom, we may find that these straight lines are associated with certain symptoms only, and we have basically we have a stepwise function, or we have two regions. People are in stage one, which could be very healthy, and people two could be in stage two, for example, Western diet. This could be Western diet, these could be vegetarian or healthy eaters or whatever. And the result is there is a transition there. We don't know the exact cause. All we know is that there's something odd happening there, and we want to take a look at our metadata to see if we can identify what the association is of these line sections to what we know about the people. And here's another one, bifidobacterium, and here we see a nice uptick, so we have too high value, and there are a bunch of conditions with bifidobacterium which are too high. And in fact, let's go over and take a look at some of them just to give you some evidence. So I hopped over to microbiome prescription, looked up bifidobacterium after I've logged in, because this section doesn't show up if you're not logged in. And now we see all the conditions where we have high bifidobacteria. And if we go up here and see, you can see all sorts of conditions have high bacteria being reported. For example, mood disorders. I can go in fact do one more. Sorry. Okay, give me a second. And we see things like asthma, we have 4 citations, depression 4 citations, epilepsy 4 suggestions, citations, etc. So the fact that we are have a high level where too much is probably not good agrees with the study showing that bifidobacteria you can have too much of it and it can cause a variety of problems, which means if you're looking at the bifidobacteria, you need to factor in whether or not you have other conditions involved. And then again, we have the low levels, and flipping back to bifidobacteria, we have a bunch of conditions where low bacteria levels are cited, like chronic fatigue syndrome, obesity, allergies. Okay. So basically what we end up doing is using this method to get a line that matches pretty closely to the actual data pattern we have seen, and where the line stops being straight at the top end or the bottom end is where we determine the reference points. If we have an oddball, which only happens for a very small number of bacteria, where we seem to have two states with different slopes and an intermediate there, we have a more complicated process. But let's not deal with that issue at the moment. But basically, it gives us a methodology to determine what values are significant or not. And the logic of it is very simple. Every person here is going to have some similarity to their neighbors. When the similarity to the neighbors starts disappearing rapidly at both ends, something seems to be off. For some bacteria, there is no disappearance or very little disappearance at the high end. Sorry, just absolutely flat. So there's only a low level. And in some cases, the low level here can go almost all the way down to zero. Each bacteria has its own distinctive pattern. This approach allows the microbiome prescription to have ranges which are based on the behavior of the bacteria coming from a particular lab. Now, the secondary aspect of it is that if we're looking at a particular condition, we can go and look at the conditions pattern, and from that one we can do a qualified range. That is, if you have asthma, then the high point which should be concerned is X, which would be different than the general population. It gives us a wonderful ability to determine ranges which are items which we should be concerned or not be concerned about this bacteria. The purpose is to identify the bacteria which are the cause of the symptoms or the diagnosis, and to focus our attention on modifying those and only those. We don't want to try fixing everything, because majority of the bacteria are innocent bystanders. We want to go after the criminals. We want to go after those who are causing disruption. So that's basically it. Logic is very straightforward. Got some mathematics to do for it, and technically the method is, the patent has been filed for it, so he's just waiting until the patent bureau approves or not approve it. I expect them to approve it. I have had like a couple of patents done to me, and the way I perceive it is chances are they will approve the patent. It is a unique methodology, and nobody else is doing it. Okay, so that's it, and have a good day.